Have you ever wondered how hydrologists turn rainfall data into river flow predictions? How we estimate floods, design dams, size drainage systems, or assess climate change impacts, all from rainfall? The answer lies in rainfall-runoff models, but here is the catch. There isn't just one type, there are many, and each one built with different assumptions, data needs, and levels of complexity. In this video, I will give you a clear, structured overview of the main types of rainfall-runoff models, how they are classified, and most importantly, when and why each one is being used. Let's get started. Simulating rainfall runoff process is one of the central challenges in hydrological engineering and water resources management. At its core, it involves transforming a stochastic meteorological input, rainfall, into a hydrological output, stream flow. This transformation is governed by a complex interaction of physical processes, including interception by vegetation, infiltration into the soil, surface and subsurface storage, evapotranspiration, and finally overland and channel flow routing. Because these processes are complex, variable in space and time, and often poorly observed, hydrologists rely on models, simplified representations of reality. To understand these models, we usually classify them along four key axes: process representation, spatial discretization, temporal scope, and treatment of uncertainty. Let's explore them. Classification based on process representation categorizes the rainfall runoff models into three groups: empirical, conceptual, and physically based models. Empirical models do not attempt to describe physical processes inside the catchment. Instead, they rely on a statistical or mathematical relationship that directly link rainfall to runoff. The key characteristics of this type are its strong dependence on historical data and the fact that the model parameters often have no physical meaning. Examples of this type are rational method, unit hydrograph, SCS curve number method, regression models, and machine learning tools such as artificial neural networks. These models are best suited for catchments with good historical data where the goal is prediction, not physical interpretation. Conceptual models represent the catchment as a set of interconnected storage reservoirs that mimic physical processes such as infiltration, percolation, and evapotranspiration. The key characteristics of this type are as follows. First, they are simplified representation of physical processes. Secondly, the parameters often represent conceptual quantities like soil moisture storage. And finally, model parameters usually require calibration. Examples of this type of models are RORB, ERBS, AWBM, HEC-HMS under conceptual mode, HBV, SAC-SMA, NAM, and tank model. These models are best suited for operational hydrology and forecasting, where some physical insight is needed but data is limited. Physically based models are built on fundamental conservation laws: mass, momentum, and energy. They aim to explicitly represent the physical processes using measurable parameters. The key characteristics of this type are high complexity and data requirements, the fact that parameters often correspond to physical properties, and calibration is still commonly required in practice. Examples include Mike-Shee and SWMM when fully physically based components are used. These models are best suited for detailed studies such as land use change, water quality analysis, and highly heterogeneous catchments. Considering the type of spatial discretization, rainfall runoff models are categorized into three groups: lumped, semi-distributed, and fully distributed models. In lumped models, the entire catchment is treated as one unit. Rainfall, soil properties, and slope are spatially averaged. These models are simple, fast in computation, with low data requirements. However, they cannot represent the spatial variability. Examples are tank model and SimHyd. These models are best suited for long-term water balance analysis, real-time forecasting in gauged catchments, and initial runoff estimations. In semi-distributed models, the catchment is divided into subcatchments or zones, each treated as lumped but routed together to the outlet. They are hydraulically connected like chain of buckets. These models have a good balance between realism and simplicity. However, they come with some shortfalls, including loss of spatial detail, subjectivity in subcatchment delineation, equiphenolity, and being inadequate for overland flow mapping. Examples are RORB, WBNM, HEC-HMS, SWMM, and SWOT. These models are best suited for standard flood estimation, large heterogeneous catchments, and reservoir inflow modeling. In distributed models, the catchment is divided into a fine grid of cells with calculations performed for every single cell, allowing water to move from one cell to another. These models offer high spatial realism and are suitable for complex rainfall and land use patterns. However, they are computationally expensive and data intensive. Examples are Mike Shee, 2Flow and HECRAS under rain on grid mode, and VFlow. These models are best suited for floodplain risk mapping, urban flash flooding, land use change studies, and water quality tracking. Based on the temporal scope, the rainfall runoff models can be classified into two main groups: event-based models and continuous models. The event-based models simulate a single storm event. They focus on surface runoff and infiltration, often neglecting evaporation and long-term soil moisture balance. Examples are RORB and WBNM. These models are best suited for estimating design storms. Continuous models, on the other hand, simulate hydrological processes over long periods of time, such as months or years. They account for water balance processes in both wet and dry periods. Most modern rainfall runoff models are capable of continuous modeling. These models are best suited for water balance studies, crop yield analysis, and drought assessment. Based on how a model treats the uncertainty, rainfall runoff models can be classified as deterministic or stochastic models. Given the same inputs, the deterministic models always produce the same output. This is the standard approach in most engineering applications, and the majority of rainfall runoff models fall in this category. These models are best suited for simple infrastructure design, operational flood forecasting, and scenario testing. The stochastic models explicitly include randomness to represent uncertainty. In this case, outputs are expressed as probability distributions, not single values. The best example of this type is RORB under Monte Carlo mode. These models are best suited for major infrastructure design, complex risk assessment, water resources reliability analysis, and finally insurance and economics assessment. As you saw, rainfall runoff models come in many forms, each designed for a specific purpose, data availability, and level of complexity. There is no single best model, only the model that best fits your problem, data, and decision context. If you found this overview helpful, please don't forget to like, subscribe, and explore our channel for more hydrology and water engineering content. See you in the next video.